Imagine an AI that actually pauses to think deeply, looping through its own neural pathways to solve complex problems instead of just regurgitating text. Welcome to our podcast, Artificial Intelligence. Papers and concepts curated by Dr. Satya Malik and narrated using AI-generated voices.
Yeah, today we are taking a deep dive into something that honestly challenges a lot of the core assumptions we have about AI.
Yeah.
It's based on a fascinating new paper called Scaling Latent Reasoning via Looped Language Models.
Right, and this comes from researchers over at ByteDance, UC Santa Cruz, and a few other institutions. And our mission for this deep dive is to really unpack this new family of models they've built, which they call Ouro.
Exactly, like the Ouroboros, that ancient symbol of the snake eating its own tail.
Which is such a perfect name, honestly, because we're going to break down how this specific architecture achieves like 2 to 3 times the parameter efficiency of standard models simply by reusing its own internal layers.
It's a huge deal
Yeah,
because it fundamentally challenges this long-standing assumption you and I talk about all the time.
that bigger is always better.
Right. For years, the dominant paradigm with these large language models has just been brute force.
Hmm.
If you want the AI to be smarter, you just add billions, well, trillions of parameters. You just keep stacking layer upon layer.
But the reality is we've reached a point where deploying those massive models requires absolutely staggering infrastructure.
Oh, yeah. The data centers, the incredible energy consumption, not to mention the severe latency issues. It creates a massive scaling bottleneck for anyone trying to actually, build real-world products.
And the other historical workaround we've seen is that inference time trick, chain of thought reasoning.
Yeah, the think step-by-step prompt.
Exactly. If you're listening and you've ever told an AI to show its work, you've used it, the model spits out these really long, rambling strings of text, basically working through the problem out loud before it gives you the final answer.
But the hidden cost there is that to do that, you have to feed all of that generated text right back into the model.
Right, which requires bloated context windows. And again, that costs massive amounts of compute and time. It's not a free lunch.
No, not at all. So what the RO models do is offer a completely different pathway, which is this concept of recurrent depth.
Okay, let's break that down for the listener. Because computing in the latent space or recurrent depth, it sounds a bit like science fiction. What does that actually look like under the hood?
So picture a core block of neural network layers. These are the mathematical filters the AI uses to process information.
Okay, got it.
In a standard model, the data passes through layer 1, then layer 2, all the way down to, say, layer 100, and out comes your answer. It's a one-way street.
You just push it straight through the pipe?
Exactly. But in the RO architecture, they use a much smaller shared stack of what they call weight-tied layers. The data passes through this core block, and then it actually loops back around to the start of that exact same block.
Oh, wow. So it uses the exact same parameters to process the data multiple times during a single forward pass.
Yes. So the model is iteratively refining its internal mathematical representation of the data, rather than generating explicit text for every single thought.
That is wild. And the results they published to back this up are seriously impressive. They released two specific models, right? RO 1.4b and RO 2.6b.
Yeah, both of them were trained on a massive 7.7 trillion tokens. And the efficiency they achieve, it completely upends the traditional scaling laws we're used to.
Like the 1.4 billion parameter model is matching standard 4 billion parameter models.
Right. And the 2.6 billion parameter one is going toe-to-toe with 8 billion parameter models. And we are talking about intensely difficult reasoning benchmarks here.
Yeah, we should definitely contextualize those benchmarks for a second. We aren't talking about basic trivia like, what's the capital of Spain?
No, they tested these on MMLU Pro, which evaluates professional level knowledge. They use BBH.
Only bench hard, right.
Exactly, which is specifically made of tasks that standard models traditionally just fail at. And Math 500, which is complex competition level math, these require deep multi-step logic.
The model isn't just recalling facts, it's actively reasoning. Let me try to visualize this. Tell me if this analogy tracks.
Sure, go for it.
It's like a student taking a really difficult physics exam. The old way of making the AI smarter was either physically growing the student a bigger brain, so adding more parameters, or giving them endless stacks of scrap paper to show all their work out loud, which is chain of thought.
Right.
But the Ouro approach is like the student just closing their eyes, sitting quietly, and turning the problem over in their head a few times before writing down a single final answer.
That's actually a very strong visual. But I would just add one crucial nuance to that.
Okay, what's that?
The student isn't just pondering aimlessly. They're actively running the problem through the exact same set of logical frameworks they already possess, just applying them deeper each time.
Before you elaborate on that, I actually have a major pushback on this whole looping idea. But first, a quick note. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
Thanks for sharing that. So what was your pushback on the looping?
Well, if you design a model to just loop endlessly, aren't you going to waste massive amounts of computing power on really simple
Oh,
questions?
I see where you're going now.
Like, if I ask this highly sophisticated looping model, what is 2 plus 2, does it really need to sit there and run its entire neural network 4 times just to tell me the answer is 4?
That is the exact trap the researchers had to avoid. And it brings us to what I think is one of the most elegant engineering solutions in the whole architecture.
Okay, what did they do?
They built in an exit gate mechanism. So the model does not loop universally for every single prompt. It employs what's called adaptive computation.
So it essentially has a way to clock out early when the actual work is done.
Exactly. And each loop, and keep in mind, these particular models are trained to perform a maximum of 4 recurrent steps. But at each step, this exit gate evaluates the current state of the data.
And what is it looking for?
It predicts an instantaneous probability that it should just terminate the loop right then and there. So if the token is simple, like your 2 plus 2 example, the exit gate triggers early, maybe after just one single loop.
Right, because it's confident it has the answer.
Yes. But if it's processing a complex mathematical proof, the gate keeps the probability of exiting low, and the data stays in the loop for the full 4 steps.
Okay, that sounds absolutely flawless in theory. But getting a neural network to honestly self-evaluate the difficulty of a problem during training, that has to be a total nightmare.
Well, it was a massive hurdle. They encountered something called the collapse problem.
The collapse problem, like the whole model just breaks down.
Not exactly breaks, but it falls into these really bad habits. If you try to train this adaptive looping using standard gradient descent,
Which is basically the process of adjusting the model's weights by following the path of least resistance to lower its error rate, right?
right, it's like water flowing downhill.
Yeah.
It always finds the easiest route. So
Yeah.
the model either gets essentially lazy, it collapses to shallow depths, exiting immediately on step 1 every single time just to minimize its computational effort.
Oh, wow. I get the laziness, but is there an opposite extreme?
Yes. Conversely, it gets overly cautious. It always defaults to the maximum number of loops.
Wait, why would it default to being overly cautious if it wants the easy way out?
Because in deep neural networks, processing data through more layers, or in this case, more loops, naturally tends to produce a more accurate prediction.
Ah, so it gets better grades if it loops more.
Exactly. The mathematical gradients naturally shift all the probability mass toward that final step. It essentially whispers to the model, hey, your loss rate is lowest if you just use all 4 loops every time, so play it safe.
So it creates a self-reinforcing loop of inefficiency.
Yeah.
It entirely stops being adaptive.
Yes. So to fix that, the teams at ByteDance and UC Santa Cruz introduce an entropy regularized objective.
Okay, entropy. In an information theory context, that's basically a measure of spread or unpredictability, right?
Precisely. By adding this specific mathematical penalty into the training process, they forced the model to maintain a balanced spread of probabilities across all the loops.
Oh, so they actively penalize the model if it collapsed all of its probability mass entirely to the final loop or entirely to the first loop.
Exactly. They made it mathematically expensive to be too lazy or too cautious.
You know, it reminds me of trying to manage a team of salaried office workers.
How so?
Well, you have this exact same collapse problem in an office. You don't want everyone getting lazy and clocking out at 10 a.m. every day, but you also don't want everyone doing unnecessary overtime until midnight just to look busy.
Right, because as the boss, you're paying for the electricity to keep the lights on.
Exactly. So you have to create an incentive structure, your entropy regularization, that encourages them to leave exactly when the actual work is done. Not a minute before, not a minute after.
That's a really fun way to frame it. Though obviously with the neural network, the incentive has to be mathematically enforced at the gradient level.
Right, of course.
They also paired this with a highly focused training stage that specifically tuned the trade-off between the compute being used and the performance gained. They painstakingly trained that exit gate to genuinely match the compute depth to the actual difficulty of the input.
Which brings up a really core question for anyone, looking at these smaller, highly efficient models. If the Ouro model is just reusing the exact same parameters over and over again, Is it actually learning more facts during these loops, or is it just getting better at utilizing the facts it already has?
That is the million-dollar question for AI scaling right now. And the researchers ran these highly controlled experiments inspired by the physics of language models framework to figure it out.
And what did they find?
The finding is definitive. Looping does not increase raw knowledge storage.
That is fascinating. So a 1.4 billion parameter model with 4 loops doesn't store any more historical dates or pop culture trivia than a standard 1.4 billion parameter model.
Not at all. The researchers confirmed a very consistent rule across the board. Both looped and non-loop models max out at storing about 2 bits of knowledge per parameter.
2 bits per parameter.
Yes, the sheer number of parameters you have is a strict physical indicator of how much raw data the model can memorize. Looping your parameters does not magically increase the size of your memory bucket.
Okay, but if it doesn't know more facts, where is that massive performance jump coming from? Why is it crushing these multi-step reasoning benchmarks and matching models 3 times its size?
It all comes down to knowledge manipulation.
Yeah.
To prove this, they tested the models using synthetic tasks.
Yeah.
One was the Mano task, which involves complex modular arithmetic. The other was multi-hop question answering.
Okay, for the listener, multi-hop QA is when you can't just look up an answer directly. The model has to find piece of knowledge, A, use that to locate piece of knowledge, B, and then connect that to piece of knowledge, C, to formulate a final answer.
Exactly. Like asking, what language is spoken in the birthplace of the author of 1984?
Right, so you have to know the author George Orwell, where he was born in India, and the language of that region. It's a chain of facts.
Yes. And the recurrent structure gives the loop LM a massive advantage in composing those atomic facts. It can navigate that complex, multi-hop logic without needing a larger parameter count.
So it doesn't need to memorize the final answer beforehand.
Exactly. It just needs to know the basic facts and the rules of logic, and it uses the iterative loops to calculate the path between them.
So it's not a bigger hard drive, it's just a vastly superior CPU.
That's a great way to put it.
And if we look back at the real-world benchmark data from the paper, this completely explains the category breakdowns on the MMLU test.
Oh, absolutely.
Because the biggest performance jumps from loop 1 to loop 4 were all in procedural tasks. Formal logic improved by over 140%. Elementary math was up 155%. But static knowledge tasks like global facts only saw an 8% bump.
Right. Because if a user asks, what is the capital of France? Looping your logic circuits 4 times isn't going to help you if your parameter weights simply do not contain the word Paris.
Yeah, you either know it or you don't.
Exactly. But if the question asks for a complex logical deduction based on a set of provided premises, looping allows the model to iteratively refine the logical steps, which yields those massive 140% improvements.
That makes total sense. But, if the model is so much better at navigating these complex multi-hop logic puzzles, I wonder how that applies to recognizing when it's being tricked.
What do you mean?
Well, a lot of safety jailbreaks are essentially just multi-hop logic puzzles designed to confuse the AI's safety guardrails. So does giving the AI a superior CPU to think deeply make it safer? Or does it make it more capable of bypassing its own safety rails?
That is a brilliant connection. And the researchers actually looked exactly at that using the HexPHI dataset.
Okay, what does that dataset test for?
It specifically tests the model against 11 different categories of harmfulness. We're talking things like hate speech, dangerous activities, and self-harm instructions.
And what was the verdict?
The remarkable finding is that as the number of recurrent steps increases, the model's harmfulness rate drops significantly. Thinking longer actually makes it safer.
Wait, really? But the Ouro models were only officially trained on a maximum of 4 recurrent steps. What happens if you push the model during inference? Like, if you force it to extrapolate and loop 5, 6, or even 8 times, does the system just break down?
Well, that is where the nuance lies. When you force the model to extrapolate beyond its trained 4 steps, its accuracy on general knowledge benchmarks does start to degrade slightly.
It gets a little confused on the facts.
Right. However, its safety profile continues to improve.
That feels entirely counterintuitive. Even when the general accuracy drops, the safety continues to go up. How did they verify why that's happening mechanically?
They use a technique called Principal Component Analysis, or PCA, on the hidden representations inside the model.
Okay, PCA. That's essentially a data visualization tool, right? It takes a massively complex, multidimensional cloud of data points and mathematically flattens it down so we can actually see the underlying patterns on a 2D graph.
That's a perfect description, yeah. They use PCA to look at how the model clusters its internal representations of benign prompts versus harmful prompts.
And what did the graph show?
What they saw was that at step 1, the boundary between safe and unsafe requests is really blurry. The data points overlap. The model is a bit confused.
Okay.
But as the loops increase to 2, 3, and 4, the model becomes much more capable of separating those clusters. The boundary becomes sharp.
So even if it starts forgetting some trivia at step 8, its internal compass for what constitutes a harmful structure remains robust.
Exactly. It actually becomes more distinct the longer it thinks.
This completely changes how we approach trust and transparency with these models. Because right now, with standard chain of thought, there is a massive problem with post hoc rationalization.
It's a huge issue.
A standard model basically decides the answer instantly in its first layer based on a gut instinct, and then uses the text generation phase just to hallucinate a plausible sounding excuse for why it picked that answer. You aren't actually seeing its real thinking process.
You've highlighted the fatal flaw of explicit text-based reasoning right there. It is often just a rationalization. Loop ELMs, on the other hand, prioritize faithfulness over rationalization.
Oh, so.
Because the reasoning happens entirely in the latent state. It's updating the actual mathematics of the hidden layers step by step. So those internal thoughts genuinely cause the final answer.
And the researchers proved this using the core question pairs dataset, didn't they?
They did, yes.
Because that dataset is notoriously full of highly ambiguous questions where you have to determine if two differently worded prompts mean the exact same thing.
Yes. And they evaluated the model's internal state at each loop using linear probes.
Let me make sure I understand linear probes. Is it sort of like hooking the model up to an fMRI machine and taking a snapshot of its brain activity at each step to see what it's thinking?
It's very similar to that, actually. A linear probe is a simple, lightweight classifier that you attach to the hidden layers of a frozen neural network.
So you aren't changing the model itself?
Right, you're just training this probe to read the internal mathematical state and translate it into a readable prediction. It allows us to literally peek inside the black box.
And what did the fMRI or the linear probe show them on those really ambiguous questions?
They could literally watch the model change its mind.
Wow.
Yeah. At loop 1, the model might heavily lean toward, yes, these two questions mean the exact same thing. But at loop 2, as it processes the subtle nuance in the phrasing, you see the internal state shift.
And then by the final loop,
By loop 4, it firmly arrives at no. This systematic disagreement across the steps proves that the internal latent thoughts are genuinely updating the decision. It is active, faithful deliberation, not just a frozen rationalization.
if we can actually trust the internal states, that seems like it would have massive bonuses for real-world deployment, especially for things like speculative decoding.
Oh, absolutely.
Because in a normal setup, you often need two completely separate models to do speculative decoding efficiently. You need a small, fast draft model to guess the next few words, and a massive verifier model to double-check if those guesses were right.
Right. It's fast, but deploying two different models is incredibly clunky.
Exactly. You're anticipating the exact architectural advantage here, aren't you?
Well, because Ouro inherently uses loops. It contains a built-in draft model.
So you just use the early loops as the drafter and the final loop as the verifier.
Precisely. You use step 1 or 2 to act as the fast draft model generating proposals. Then, you use the final step 4 as the verifier. You achieve all the speed benefits of speculative decoding without ever needing a second model.
That is brilliant.
It makes inference highly efficient. Moreover, it natively supports preemptive safety checks. You can screen those draft tokens for safety violations in the early loops before they are ever verified or shown to the user.
It really is a total paradigm shift in how we build and deploy these reasoning systems.
The implications for parameter efficiency and transparent reasoning are truly profound. It's a very exciting time.
Thank you so much for joining us on this exploration of the Ouro models. It's been incredibly eye-opening. If you enjoyed this breakdown, please make sure to subscribe to the show for more deep dives into the most cutting-edge AI concepts.
Thanks for having me. It was a great conversation.
As we wrap up, I want to leave you, the listener, with a final thought to mull over. For the last few years, the entire tech industry has operated on the belief that reaching artificial general intelligence requires building massive data centers the size of cities, consuming the power of small nations just to stuff more and more parameters into giant models. But if loop LMs prove that human-level reasoning is actually about dynamically manipulating a smaller, highly curated set of facts through iterative internal loops, could the most powerful AI of the future be something that fits effortlessly onto the phone in your pocket, spending its time thinking rather than just storing?